So in many applications, we have a normal random process as noise added to our signals, or a normally distributed random process and stationary. So in those cases, if you have a normal random process with zero mean and an autocorrelation function or x of 2, which means that this random process is wide sense stationary. And then if you have a memoryless system, a memoryless time invariant system, time invariant. So Bussgang theorem, which we give it as an example, first of all, we know that because memoryless time invariant, x of t and y of t are jointly strictly sense stationary. But this theorem, because the input is normal and zero mean, we want to calculate the cross correlation between input and output. And in this example, we prove that this is interestingly equal to Rx of 2. That means that the autocorrelation function of the input and output is equal to the autocorrelation function of the input times a constant. This constant can be sometimes negative, sometimes 0, sometimes 1, etc. And these constant can be easily calculated. So the proof is very easy. The two random variables x of t and x of t plus 2 are jointly normal with zero mean and covariance of that. Now, for any two jointly normal random variable w and z with a covariance r and any function of h of w and z, in one of the previous chapters, it was one exercise, you have these relationships. So any function of any two jointly normal random variable, if they are jointly normal with a covariance of r, the derivative of any statistics like that n times with respect to r can be calculated using this one. The proof of this is easy, particularly if you prove it for n equal 1. Is very trivial for n equal 2, etc., because you apply the same theorem n times. So this theorem, if n is equal 1, is same as having n for n equal to n times. Now, so because here I have a particular function, my function here is going to be equal to x times g of y, okay? So if this is my function, and if I calculate a mean of that, okay, and if I calculate derivative of these with respect to r, cross correlation of x and y, I could apply this theorem, or I could apply this n times, but I applied only once. So what happens is that this guy, if I put x equal to x of t, and y, if I put it like this is t and y is at time t plus 2, then I apply it here, and then you get this guy, and then you get this one. And interestingly, when you simplify this guy, derivative of these simplifies to just derivative of, because this becomes 1 with respect to this one, and derivative of these will become derivative of g. So in other words, the cross correlation between the input and output is equal to k times this one, and k is just, you calculate this function g, derivative g prime, and then you replace it by x at time t, and then this will become a random variable, calculate mean of that, which is easy, and then you get these constants. So these constants become calculated. Details of the proof of the Bussgang theorem here, these details are not important. What I need is a normal wide sense stationary random process with mean 0, and this function, the autocorrelation of the input and the cross correlation of the output. These two guys, they are proportional together. So in other words, the cross correlation of the output with the input is equal to a constant term times the autocorrelation of the input. Remember that these guys are xx 2 is equal to mean of the sample of this one x at time t plus 2 and x at time t. And this guy is equal to, by definition, mean of this guy x at time t plus 2 and y at time t. So this Bussgang theorem is very applicable anywhere you have Gaussian noise, a stationary Gaussian noise at the input, and then you can easily apply it.